Is it okay? Can you guys hear me? Okay, let's continue. I will try to cover a lot of stuff today. Obviously, will not cover. There were several questions at the end of my previous lecture, some from Leo, about condensation energy. It's all resolved. Everything is fine. If you want to know details, ask me, and I will tell you a little bit more in details. But right now, I want to move a little bit further, and we all never finish lecture number 1 when we're supposed to start lecture number 2. I'm not exception. So I will take 5-10 minutes just to finish what I wanted to say in lecture 1, and then we'll move on. What I want to say is rather simple stuff, that when we solve, remember what we're doing. We're doing at this stage what is normally called BSS theory of superconductivity, although what precisely means these words mean, it's subject to interpretation. But I made assumption that we will question later on today as a wrong assumption that effective interaction, constant interaction that I put in is negative, which means attraction. And ask the question, when interaction is negative, what happens? And what we discussed in my first lecture is that when interaction is negative, no matter how small this interaction is, you get instability of a system. Fermions don't want to live in a Fermi liquid. They want to form bound states, and they want to form a condensate of these bound pairs. Parameter which I will be using, lambda, which is mu over 2 pi square pf, is just to make this dimensionless in 3 dimensions. If it's 2 dimensions, it's just density of states m over 2 pi. It's all details. BSS theory of superconductivity has one disadvantage. It will not tell you what the critical temperature is. Why? Because the theory as formulated with constant interaction has ultraviolet singularity, and you need to cut this singularity. So standard assumption that is made in the first papers on the subject was that let's take interaction U without specifying where it comes from. I'll put mod U because we're talking about repulsive and about attractive interaction. I will keep it constant up to some energy scale and then make it drop to 0. And I call this energy scale omega naught if this is generally some energy. If you don't do this, you formally get infinity in the theory. As a result of this, when you calculate TC, superconducting instability temperature, where, remember we discussed this is where the system develops instability at 0 total momentum of a pair, and when fermions form bound states. You get, this is exactly as the scale, remember that was the scale where the pole was in the upper half plane. I labeled the scale as B. This scale, I'll put it proportionality, omega naught times e to minus 1 over lambda. This is fundamental. This is exponential dependence on the coupling constant, and we know where it comes from. It comes from the fact that when we do calculations, we have logarithmical singularity of the response in a particle-particle channel. If we want to calculate order parameters that I introduced, delta, B-Dagger average, it also scales as omega naught e to minus 1 over lambda. And again, if you ask theory, can you give me numbers? Theory will tell you, no, I cannot give you numbers. I don't know what is this quantity. It's some arbitrary parameter in the system. We just put it by hand. Nevertheless, beauty of BSS theory, and really fantastic beauty of BSS theory, is that if you take ratio of these two guys, normally it's set as 2 delta over TC, you get universal number that doesn't depend on omega naught. And this is what experimentalists, of course, tried and get 53 in 3 dimensions. If you take D wave superconductivity and do exactly the same, you get number 4.29, and it's not a big deal. Yes?
Can you comment how much does that number vary from material to material?
It's a good question. As far as I understand, in conventional superconductors, this number is pretty close to reality. Yes, even in cuprates, 2 delta over Tc 4 times 2 is the result that was found in overdoped cuprates. So it's not that bad in this regard. Yes? Oh, you're asking about what happens when you have more than one Fermi surface, more than one gap. Then average value, then it should be on average value of the order parameter, but some of it can be larger, some can be smaller. And that's precisely the story in iron-based, yes. There is strong coupling version of BCS theory, and we'll hopefully come to this strong coupling version at the next lecture, in fact. This number can go can be as high as 11. So yes, in strong coupling versions, the number goes up. But at this stage, I want to make link to the next points that I want to discuss quickly. And there is another quantity which is completely universal in BCS theory. If you look at specific heat as a function of temperature, and let's look at specific heat coefficient, C over T. In the normal state, Fermi liquid, specific heat is linear in T. Specific heat coefficient is a constant. You approach Tc, it jumps, and then it starts going down. The amount of jump divided by amount of specific heat right at this point is universal ratio. Specific heat at Tc minus naught minus specific heat of Tc plus naught divided by specific heat of Tc plus naught is equal to 1,443. And even this number is expressed in terms of zeta function, etc. So this universal number, this is another universal number. Universal means they express in terms of special functions. Okay, this is just to remind you that BCS theory has disadvantage. It doesn't tell you what Tc is, and this will be cured by more sophisticated theories like the Ashberg theory, but it gives you universal ratios. Very good. Sorry?
This is in mean field.
This is all in mean field, yeah. That's all in mean field. As I said, you go beyond mean fields, the number changes, but in mean fields, the number is like this. But there is one interesting aspect of the story that was raised, in fact, in 60s of last century. Is it always true? Can we do a little bit better than this, even within BCS theory, without changing anything? And the answer is surprisingly yes. We can get, it's not that much important for studies of strongly correlated electron system, but what I will tell you in a minute is sort of important for studies of superfluidity in the mixtures of helium-3 and helium-4. And the question is this. Suppose that I get what I just showed you. Let's suppose that interaction is a constant, and let it be constant up to very large scale, such that scale of Fermi energy will be somewhere here. So these are all energies up to Fermi energy. In other words, let me assume that interaction is constant up to very large scale. Question, can I express Tc in a universal form in terms of observable quantities? And the answer is yes, I can. And the point is, the one that was then later resurfaced in the issue of BCS to BEC crossover is what is superconductivity with respect to bound state of affairs in general. And remember how we find all this. We look into particle-particle channel. We calculated essentially susceptibility in a particle-particle channel. And elements that we were doing, remember there was interaction. I wrote this as a full interaction. And the important element that we considered was the renormalization of the Bayer interaction in a particle-particle channel. There is also anti-symmetrized components that we discuss in 5 minutes from now. But at this moment, all I want to say, you have a particle-particle pair in a situation when we have momenta k and minus k, And also frequencies omega k and minus omega k means I put both momenta and frequency to external total momentum and total frequency to 0. What I have here is I have L omega L minus L minus omega L, and I have to integrate over these two green functions. And I have to do this in a situation when I have Fermi surface. So taking for simplicity parabolic dispersion, this is our Fermi energy equal at 0 temperature to chemical potential. And superconductivity comes from the states below Fermi surface and from the states above Fermi surface. These two fermions should have pulses in different half planes because one has frequency omega and another minus omega, we're essentially guarantees that they have pulses in the opposite half planes everywhere. So we integrate over L, over all momenta, translate this into integration over energy by introducing integration of momentum. D dimension goes into density states integral over energy. I integrate from here, from 0 to infinity.
So plus omega related to the chemical potential is above and minus.
Yes, but remember from the very beginning, I said I always consider when I write epsilon with respect to chemical potential. So dispersion is always with respect to chemical potential. Very good. Here's a simple point. That we have to integrate, let's put it G, L, G minus L. You understand what it means. Both momentum and frequencies are here. Let me split this integral. And I do it this way. I will subtract and add one quantity to this integral. If I'm at energies, epsilon L, which are much larger than Fermi energy, then essentially the very fact that you just asked me whether or not the system has a chemical potential is irrelevant. And then we go to the essentially not a superconducting problem. We go to the problem of just interaction or scattering between two particles in a vacuum. So we no longer have a field Fermi C. Again, I want to go to energies well above this scale. Then I essentially deal with two particles in a vacuum. And let's start the phrase again. Then we know that Schrödinger equation can be formulated by summing up particular set of graphs. Which ones? The same ones. Why? Because any other diagrams requires one particle to be above chemical potential, another below chemical potential. If chemical potential is 0, we just don't have the space. So meaning of what I'm just saying right now is that part of this integral contains information not about superconductivity. It contains information about behavior of two particles in a vacuum. And behavior of two particles in a vacuum is quantum mechanics. This is what translates interactions into scattering amplitude. Because if I ask a simple question, is interaction measurable? The answer is no, interaction is not measurable. Why? Because if particles interact once, no one forbids them to interact twice, 3 times, 4 times, etc. So what is really measurable quantity is a scattering length, quantum mechanical property, which in case of constant interaction, just take it for simplicity, reduces to what is called, scattering amplitude, which in case of constant interaction reduces to quantity which is called scattering length. That's all quantum mechanics. So T matrix in more general case, yes. So what I want to do, I want to subtract GL mu, G minus L mu. Mu means chemical potential. GL0, G minus L0, and add GL0, G minus L0. So I subtracted and add the same particle-particle contribution, but at 0 chemical potential. And this part is what eventually transforms me interaction into scattering length. And this is now convergent integral. Because if I go to large energies, the only difference between these two quantities is chemical potential. If I go to high energies, then the two quantities are almost the same, and you can check explicitly that now I can integrate to infinity, and this quantity is all convergent. It's convergent at energies compared to Fermi energy. without going into details of these calculations, let me tell you the answer. So this guy is responsible for what you know from quantum mechanics, that scattering length is equal to mu over 4 pi, 1 plus corrections. What are these corrections? It's these terms. These are corrections. This is what transforms interaction into scattering length. The rest is now fully convergent. As a result, you can write this expression for TC. It's the same expression. I'm not doing anything different. But previously, it was expression in terms of some unknown scale, with known coefficient but unknown scale. Now it's expression like this. TC is equal to 0.277 in 3 dimensions, Fermi energy for parabolic dispersion, e to minus pi over 2 mod A times PF. Exact. There is no artificial parameter, nothing. But of course, it's transforming one problem into the other. Because then somebody can ask, can you calculate A? No. Because in order to calculate A, I have to avoid ultraviolet singularities. Then the same scale appears in A. But the argument here is this is a measurable quantity. You can take this quantity from experiment. And in fact, if you look at papers on superconductivity somewhere in 60s, they all express TC always, no matter what they do. Not in terms of interaction, but in terms of scattering length. At that time, it was just common practice. So statement is that this is a measurable quantity. So whatever it is, you can get it from experiment. And then here's the number. Yeah.
And where did the log come from? Where is the Cooper log hidden in this calculation?
In the first, it's here. It's here. Cooper log is integral close to chemical potential. It's all here. This term is needed to cancel out this integral. Basically, what we get integral dx over x. There is a lower limit that gives you Cooper log, but there's an upper limit. And this guy cancels out contribution from the upper limit. This is how you get log, but it's log with universal prefactor or universal argument in the log. Okay, good. So this is just to let you know that in principle, even in BSS theory, you can calculate superconducting temperature exactly. Yes? If EF is much smaller than omega naught, this is what I said from the beginning. If EF is not smaller than omega naught, you cannot do it. You can, but it's completely useless. Then you can calculate everything even without doing what I'm doing. Okay, at this stage.
Where that assumption came in?
Sorry?
Where did that assumption come in?
Which assumption?
Yeah.
Oh, because I need to, basically what I need to do, I need to have a situation when this integral is, the one I just erased, difference between two terms, is completely confined at EF. It should have some own universal scale. I should be able, what I want to do is to integrate here from 0 to infinity, meaning that omega naught I put to infinity. This is what I do. Otherwise, basically what I put here is just will be some function of omega naught and EF. Still convergent integral, but ugly expression.
Does any conventional electron funnel superconductor fits this formula, or the fact that
you can take, if you want, you can take electron funnel interaction and fit into this formula. You can do it, but you don't need to. Like the electron funnel interaction, we get the result without this.
much more here?
If you have omega naught much smaller than AF, you don't need to do what I just did. Yes.
Just a comment that, in cold atoms,
Yeah.
fermionic gases, omega is effectively infinite. And the interaction there is a Peshbach-Resonant interaction, and then it's exactly fit to these formulas.
Yeah.
very well.
Mhm.
Yeah.
Yeah. So
Yeah.
It's really expressed in terms of single particle scattering length that they measure independently in a very dilute limit.
And this formula works pretty well. Yeah. Yeah. Okay, guys. Sorry. Yeah.
I was just going to ask, in what ways is it any different to say how people treat problems in high energy physics where you have to do renormalization and exchange something for a renormalization scale for an experimental measurable?
Short answer, yes, but long answer, let's talk. Yeah, just because what I want to do now is to say, okay, guys, you know how is this? You all watch this. It's a game Who Wants to Be Millionaire with celebrities. So for the first 15 minutes, all lights are on. The celebrities are asked questions, what is 2 plus 2? The next question, what is 3 plus 3? If they go through this stage and give you correct answers, then the lights are dimmed, and now the real questions start. So we'll dim the lights, and we start now answering real questions. And real question is this. How? So far, I just said, close your eyes, assume that interaction is attractive, do calculations. But you obviously have a question. Why? How to get this interaction repulsive? And we'll do this in several stages. And let's start with stage 1, like this. Yes, when interaction U is a constant, I cannot say much, except for close your eyes and assume that it's attractive. It's repulsive in reality. Let's do one first step. Let's assume that interaction is not a constant, that we have some interaction, and at this stage, I will not play the games that are played nowadays with twisted materials when interaction get dressed by coherence factors, and coherence factors know separately about momentum K and P. What I want to do is consider just more simple case when this is some interaction as a function of K minus P. Interaction as a function of momentum transfer. Think about Coulomb interaction as a function of momentum transfer. You remember where we started last time, and there was a number of questions why the hell we are doing what we are doing, when I said that what you need for superconductivity is what is called effective antisymmetrized vortex. And this was, let me write it down, UK minus P delta alpha beta delta gamma delta, when alpha beta gamma delta are spin indices for these fermions, minus U of K plus P delta alpha delta delta beta gamma, which happens when I just interchange these two fermions. When I interchange these two fermions, I obviously change the overall sign of the interaction. We did this, and we said if U is constant, all we get from this combination of delta function is spin singlet combination, which means that all this pairing state is a state with a singlet combination of two fermions, which is obvious because order parameter was in the form B dagger K, B minus K dagger, alpha beta. If I interchange, I call this delta, and then put index K, meaning that it was a constant. If I interchange these two fermions, I must change sign, and spin singlet configuration exactly did this job. So in reality, I have to write down delta times delta I sigma Y alpha beta, which is singlet combination. When interaction is a function of K minus P, the very first thing we can do is to split interaction into two components. It can be done in 1 second and just writing one line here, UK minus P plus UK plus P over 2 delta alpha beta delta gamma delta plus delta alpha delta delta beta gamma plus U K minus P minus U of K plus P over 2. And there is a sign minus between two delta functions, alpha beta gamma delta minus delta alpha delta delta beta gamma. This is just trivial rewriting, right? But now, play the game, right? Who wants to be a millionaire? So what is this? Did I put? No, I put obviously wrong. It should be minus sign here, and it should be plus sign here. Sorry. Guys, at this stage, you see better than I see what I'm writing. So what is this? Singlet combination, right? We can even write it as singlet. It's I sigma Y alpha gamma I sigma Y beta delta. Product of two singlet combinations. What is this? This is triplet combination, right? So we split interaction into singlet part and into triplet part. For constant use, this triplet part simply doesn't exist, but it generally exists when interaction is a function of momentum transfer. Very good. So this can be easily written as I sigma x alpha gamma, I sigma x beta delta. Very good. So we get one more thing compared to what we did before. One extra thing compared to what we did before. We said that general interaction can be in a singlet channel or it can be in a triplet channel. And just naively, if interaction is repulsive U, you may say, well, we know for sure this is just U, this repulsion. But if interaction is a function of momentum transfer, do we know what this quantity is? Whether it's attractive or repulsive? It's not guaranteed from the beginning, right? We need to specify what's the form of U of k minus p for this, right? Okay, going along this line, I want to do it even a little bit better. So the same formula, I will just do simple rewriting of this formula, but I want to do it this way. I want to do interaction, take interaction, U of k minus p, and ask what k and what p I need. Well, we know that pairing is at weak coupling, is a consequence of this Cooper logarithm. We discussed it here. Cooper logarithm comes from the interaction near the Fermi surface, when both momenta are close to kf. So let me take this interaction as a function of the angle. This is my Fermi surface, this is kf. This is my k, this is my p. Deviation of this momenta from the Fermi surface is small. I don't need it because I have logarithmical singularity. I don't want to disturb this logarithmical singularity in any way. So I put both of them on the Fermi surface, and then interaction will be a function of angle between these two fermions. As any function of angle, talking for next 15 minutes about isotropic system, this interaction can be expanded in angular harmonics, angular momentum harmonics. What are eigenfunctions of angular momentum harmonics in 3 dimensions? Well, Legendre polynomial, I would put it this way. And in 2 dimensions? E to I m theta. So let's do it in 3 dimensions. It will be sum over L, 2L plus 1. Then let's write down UL, and then PL of cosine theta, which are Legendre polynomial. Very good. First Legendre polynomial is 1, second Legendre polynomial is cosine theta. The third one is 3 cosine squared theta minus 1. And then we'll ask what the next one is, because I don't remember. So we expand. And then it's obvious what we get. For this guy, we get only even components. Why? Because changing p to minus p changes angle theta to p minus theta, and all odd harmonics of Legendre polynomial are odd in theta, or even harmonics are even in theta. So in this term, you only keep even harmonics. In this term, you only keep odd harmonics, right? So then you can write down very easily what happens is that you basically get, but we don't need to write it. This guy give you, let's write it here. This give you even L. This guy give you odd L. Okay, and now, fantastic thing. This gamma is also a function of theta. This guy is a function of theta. This guy is a function of pi minus theta, which is also a function of theta, right? So why don't I take this guy and expand it in Legendre harmonics? So I can take any function of theta and expand an eigenfunction of momenta. So this gamma, let me use notation U bar for the expansion of gamma. So gamma will be equal to sum over L 2L plus 1, U bar L, and then PL of cosine theta. And then, of course, all these combinations of delta functions, which basically at this stage we can easily say if it's even L, we take this guy. If it's all L, we take this guy. And we know that we need to multiply each by the corresponding either singlet or triplet combination of delta functions. So in fact, anti-symmetrization did its job. It just said that if you want spin singlet, if the state is spin singlet, that this is even function of k. If the state is spin triplet, notice that this guy changes sign when I change the sign of either k or p. So to force approximation, this is like kp term. Odd and k, odd and p. Very good. What is the fantastic thing? Fantastic thing is that this guy is the sum over L. This guy, well, basically this guy is the sum over even L. This guy over sum over all L. And, sorry?
Odd L.
Odd L, I said, yeah, odd L. And we know that we need to solve, this was, sorry, I'm running ahead of myself. So, I'm sorry, I made one logical. That's not what I meant, I'm sorry. Now what I want to do, I'm sorry, I just logically said, run ahead of myself. So this is my gamma, this is my initial interaction. Now I put it in this ladder of particle-particle diagrams. When I sum all of these diagrams, so what I do, remember what we need to do. We need to, with each term in this series, we need to add diagrams like this, diagrams like that, etc., etc. And this is how we obtain fully dressed interaction, right? We start with the bare one, we obtain fully dressed interaction, we anti-symmetrize it, we write it exactly the same form, only now these guys are fully dressed interactions, right? Let me now call gamma bar as fully dressed. And I write fully dressed interaction in terms of fully dressed u of k minus p and fully dressed u of k plus p. I can always do this. Because when I anti-symmetrized, I add with negative sign fully dressed interaction as a function of k plus p rather than k minus p. So I have exactly the same expression for gamma bar instead of gamma, only these guys are now fully dressed. So let me take now fully dressed interaction, which I call u bar of k minus p, and now expand it in harmonics to L plus 1, ul bar, pl of cosine theta. And, you know, yes? Where I have it? No, I think I already erased it, but I have this one. Yeah, this basically is this original expression, yes. Any question? Okay. So I hope that I didn't confuse you. So we write down gamma this way. I expand u in spherical harmonics. So gamma obviously is the sum of spherical harmonics. Then I said, let's put everything in a particle-particle ladder. We don't know how to do summation originally. We know how to do it for Hubbard U, but for full interaction, it's a complicated problem. But I just said, let me call the result U bar, just call the result U bar of the summation, expand in terms of harmonics. And I want to know what's the relation between UL and all harmonics that we have here, how it works. And it turns out that, I call it really fantastic property, that there is no integral relation, there is simple algebraic relation. Namely, U bar with harmonic L is related only to UL, but not to sum over L prime, U over L prime, which by itself is interesting stuff. Look, you put here, let's write momentum here, K, P, let's put it here, sorry, K, P, M, not to confuse with L here. So you get interaction U of K minus M, you get interaction U of M minus P. You need to sum over all M, and you don't know what U is. It turns out that by wonderful property, orthogonal property of Legendre polynomials, you can all have linear relation between UL and UL bar, and relation is just the same as we get for constant Hubbard U. It will be 1 plus M UL over 2 pi square PF, and then log, let me still call it log omega, not divided by mod omega, just to keep something under the log. It's exactly the same relation that we had last time for Hubbard U, but now this relation holds for arbitrary angular component of the interaction. And now let's read this formula. This formula tells you that condition for superconductivity is substantially diluted compared to the phrase interaction must be attractive or repulsive, because you may have interaction, let's take this interaction, which contain, let's assume fantastic case, which contain all components that are repulsive. Active component, 1 out of infinite number. It's sufficient to have instability such that UL bar will go to infinity when this guy is negative because of the log. And once one component of full U goes to, what's here small u, one component of this guy goes to infinity, it means the full U also goes to infinity, right? One term of the series becomes infinite, the whole series becomes infinite. Which means that condition for superconductivity, we need to have attraction and just one component of the interaction. And this was a big step. I think it was found somewhere around early 60s. In fact, the story how it was found, a story on its own. It was found by 2 independent groups. One was Landau and Pitaevsky in Soviet Union. Another was Anderson working with interesting guy. His name is Morel. You never heard about him, right? Or some of you may heard. This guy has interesting, yes, it's Anderson Morel. You know who Morel was? Morel was a clerk at French embassy in Washington, in New York, French consulate in New York. He was working as a clerk, but he was interested in physics. So on weekends, he was traveling to Princeton to work with Phil Anderson. And this is how Anderson Morel paper came in. I don't know what happened with this person afterwards. Probably he didn't publish much about physics later. Okay, let's go there. Why this is interesting? By the following reason. So now we are at the situation. So first step was to split interactions into singlet and triplet components. Second step was to split it further into partial components with a different angular momentum. And statement is we need to have one negative. It will be enough for superconductivity. Now we go to next step. And next step is this. We can ask a question. Let's take known interaction and calculate these components. A known interaction is Coulomb interaction. Let's take interaction U, which is 1 over R, which goes as 1 over Q squared. And Q is K minus P, so it's 1 over K minus P squared. As I said, both K and P are on the Fermi surface. This is a function of the angle expanded in Legendre polynomial. Just let me do it and then, do you know what the result will be? If I just expand this function in Legendre polynomial. I'm interested in sign, right? The only thing I'm interested in, will there be any negative component? The answer is no. There will be no negative component. Yes, your question.
So the reason only the SC equals 0 term appeared for the triplet was that you still started from a Hubbard-like interaction.
No. Oh, sorry. Say it again. Maybe I'm thinking.
SC equals 0 component appears for triplet. Is that you still started from the Hubbard-like interaction, right?
In some sense, yes. Sorry. In some sense, yes. But I prefer not to emphasize this. But at the end of the day, yes, of course.
Yeah, in this example. But then when you're replacing U of Q by one of yeah, so I would imagine that, this kind of interaction would come from a Coulomb, like density-density interaction, which is not a Hubbard. I mean, then you have other terms, like not only Hubbard.
That's exactly what I'm talking about. It's exactly what I'm talking about.
So in this case, you are just replacing the Hubbard u of q by 1/q squared, right?
I just said, let's forget about Hubbard. Let's just take Coulomb interaction.
Okay.
Let's take this function of the angle.
Yeah.
Let's integrate with Legendre polynomial. Let's see what the coefficients are.
Still working with so you're not talking about density-density interaction. That's what
I'm talking about density-density interaction, but density-density interaction with some momentum transfer.
But okay, I see.
It's still interaction of density at point R and density of point R prime.
Okay.
Yes.
So it seems like, there's two things going on here.
Yes.
One is the breaking up of, whatever the, Cooper, the Slaughter series into angular momentum channels.
Mm-hmm.
So that happens always, and that's just guaranteed by rotational invariance.
Yes.
But the second thing is whether this thing geometrically resums. And I think the second thing only happens if you assume you approximate u as a product of like k dot p or.
No.
It's not a geometric series otherwise.
So this was the whole point, that it looks like they're not geometric series. Nevertheless, this works. Nevertheless, when you try to write down, yes, it looks like u, again, k minus m, interaction u of k minus m, u of m minus p is a complex expression you need to integrate over m. But because of orthogonality properties of Legendre polynomials, it goes back into geometrical series. And that was the result. I mean, it's not trivial result. This is what this guy found. Okay, if you don't mind, let's move on. But still interrupt me with questions. I still have 2 more lectures to give, right? Yeah, go ahead.
Conserve the angular momentum of the pair wave function.
Each component of the interaction conserves angular momentum. Right, the interaction can be in different channels. Yeah. Yeah. Okay, yeah.
Maybe you'll discuss this later, but how fragile is this to any anisotropy?
I'll discuss it later. We'll really discuss it, yes. You guys are running ahead of train. This will be hopefully in the next 10 minutes. You're absolutely right. You're absolutely right. But we'll come to this. Actually, we're coming to this right now. So Coulomb interaction. Claim is that all UL are positive. We didn't gain anything. Okay, we know that this is not entirely correct formula, that there is a screening. So let's open up textbooks in a simple way and go into Yukawa screening. So interaction is now 1/r e to minus r over xi. And this gives you, I'm doing everything in 3 dimensions, q squared plus xi minus 2. Different function, expanded Legendre polynomials, look what coefficients are. And these coefficients are UL positive. So, that's crying face, right? We didn't get anything. We spent 45 minutes and didn't get anything. But this is not the whole story. And I'm sure that definitely some of you know what the next stage is. Is it the full screening or there is something more in the screening? Oscillations, right? Friedel oscillations, right? So what's the form of screen U of Q, U of R? U of R goes as 1/r e to minus r over xi, and there is a term cosine 2kfr over, if I put it r squared, it should be 1/r cube at large distances. I guess I'm not making a mistake here. There is another thing, interaction that was originally 1/r, that is u as a function of r, gets screened in a conventional way, as Yukawa screening. It becomes much more decaying as a function of r because of this exponent. But then at large distances, on top of this, we start seeing oscillations, and we get something like this. And then there is a question. Negative components that you get here from oscillations is nothing but overscreening. Of course, for any oscillating part, there is also a component with underscreening. And so the question is, when we include this part, what about this component, U of L? And this brings me to what is called Kohn-Luttinger mechanism of superconductivity. And this mechanism of superconductivity is this. Let's accurately, really rigorously consider the effect of screening. Yeah. Just by the very fact that occasionally interaction becomes negative means overscreening. That's just simple definition of the word overscreening. I'm coming to a point where it all comes from. So we need to go back and ask ourselves one question. Oops, sorry. Where this Friedel oscillation come from? And they come from the fact that when we calculate screening, and then we need to calculate screening, a simple case, in the simplest case, I remember your question. So in the simplest case, we say, well, there is interaction between particles, and then we start adding polarization bubbles, and we add two bubbles, etc. And this all goes on the name of RPA. So this is how we normally describe screening, by adding more and more particle Hall bubbles. Let's look into this object. This object can be calculated, and let's not go into that much details how to calculate this object. It's a product of two green functions. There is external momentum k minus p coming in here. Frequencies, I take both external fermions on the Fermi surface, so their frequencies are 0. So external frequency is 0. So which means that I need to take these two green functions, integrate them over frequency, use all these rules of diagrammatic technique, which we'll not discuss here, and get the result. And the screening comes from what we call polarization bubble. Particle Hall polarization bubble as a function of momentum q. This is k, this is p. Q is equal to k minus p or p minus k. It doesn't matter because everything depends on modulus of q. Let's see how this quantity behaves. You can calculate this quantity explicitly for free fermions, and this quantity is equal to MPF over 2 pi square, 1/2 plus 1 minus x squared. I will tell you in a second what x is, over 4x log 1 plus x, 1 minus x, when x is equal to q over 2pf, or 2k, we call it k. When x goes to 0, q goes to 0, this quantity gives you 1/2, at the time you get 1, and this is what gives you standard conventional Yukawa screening, constant. But now you look at this function as a function of q, and you find that there is something interesting going on near momentum 2kf when x is close to 1. By itself, function is completely regular. I mean, that function doesn't have any jump or anything. We can erase this. But when you look at derivatives of the function, you find that derivatives of the function is singular. When you expand this function near x equal to 1, you find that pi gives you some constant, and the next term will be 1 minus x log 2 divided by 1 minus x mod. If I'm close to q equal to 2pf. This x log 1 minus x log 1 minus x is again a singularity in the derivative, very similar to singularity that Alan was talking about yesterday as a self-energy for Dirac fermions. It was k log k, here is 1 minus x log x. What it means, if you look now into, if you put this polarization operator into the expression that effective interaction just from this set of bubbles will be equal to 1 over q squared plus pi. I don't care at this stage about sign. I hope that, yeah, the sign is plus here, so plus pi. So you get a constant at q equal to 0. That gives you a standard expression, which I had here, q squared plus constant. But if you now take the full expression and then take Fourier transform of this expression, all you have to do is to take Fourier transform. You find this. You find oscillations. So oscillation comes from singularity of the polarization bubble. So Kohn and Lattinger ask a question. Can we rigorously check whether this singularity in the polarization bubble give rise to some attraction, some component of interaction that become attractive? And in doing this, let's erase this because I will use it, but it doesn't matter. In doing this, let's do one procedure which actually is more generic than Kohn-Lattinger approach. And procedure is this. Let's split all diagrams that we can write. There was a question. I only chosen this for the renormalization of the interactions that was originally just simply u of k minus p. What about this? What about this? Etc., etc. They're there. They're not logarithmical, but they're there. So the first idea is let's split all possible processes. These are called diagrams, but I don't want to use diagrams. Let's call them processes. Let's split all processes into two parts. We select all graphs that cannot be cut along vertical line that involves two momenta m and minus m with arrows pointing into the same direction. This is called irreducible interaction in a particle-Hall channel. High-energy people use it all the time. So what I want to do, I want to write fully dressed interaction. Remember, I was forced last time to explicitly say that this is wavy line. So this full interaction will be equal to, I'll put it like this stuff, meaning all graphs except for particle-Hall channel. So except for particle-particle channel. This, but not this one. Plus this one, plus you see, this diagram is reducible. I can cut it along horizontal vertical line with two momenta, m and minus m and errors in the same direction. Here I can do it twice. I can do this all the time. So what I will be focusing is irreducible interaction, because this is what we are interested in. This we know, this gives you Cooper logarithm. So when we say that coefficient UL need to be negative, we mean this, right? We mean all renormalizations which do not involve Cooper logarithm, because Cooper logarithm give us denominator. This we get by summing up Cooper series, right? Very good. So this is point number one. Point number two, and for this I probably will go here. Point number two. Let's write diagrams for this irreducible vertex. So we do it like this. Of course, we get original one. It's part of irreducible vertex. What else we get? We get this. We get this. We get this. We get this. And that's all is the second order. Plus we get third order, fourth order, etc., graph. Kohn and Lattinger did accurate calculation by saying, let's rigorously include the effect of x log x or y log y form of the polarization bubble. So they said, let's, on top of this, consider every wavy line that's put here as secondly reducible interaction. I mean, including all graphs that doesn't contain this extra singular part in polarization bubble. Let's not do this. This will bring us for extra 10 minutes of discussion. So let me show you where the effect comes from. So what I will do, I will take interaction u of k minus p. We already know what happens when we add irreducible, when we add anti-symmetrized interaction. It's just splitting into singlet and triplet. So I take interaction like this. And I want to calculate second order graphs, all second order graphs. But, and there was a question about, so the second part of your question. Look, this is polarization bubble, P, K minus P, right? K and P. It is singular when K minus P is equal to 2KF, right? Agree? What we have here? Look, this is K, this is P. So we have two green functions here. What's the difference between moment of these two green functions? K minus P. So it's the same guy, which means that if you want to include this, you also have to include this. They're the same. What is this guy? This guy and this guy are the same, right? They just come with a factor of 2. But what is this guy? K, P, these are two fermionic momenta. It looks like particle-particle channel, but it's cross diagram. So it's actually particle hole. Maybe somebody knows. Maybe somebody has a very sharp eye. This has particle hole polarization bubble as function of what? Its function, this will be again polarization bubble of K minus P, and this will be polarization bubble of K plus P. Not minus, plus. Because K by interaction is related to minus P here. So you can just do simple momentum conservation counting, and you find that it's K plus P. Should I include this guy? The answer is yes. Why? It's the same formula, right? Only now Q is K plus P, right? So when K plus P is equal to KF? Well, when both momenta are parallel, right? When angle is theta equal to 0. But it still has the same singularity. So all these graphs have the same singularity. Let me write down to you what the result is. So what I will do this. I will write one formula that will go before I will write the final result. And the formula which I will do this. I will take polarization P particle hole of K minus P. Q is K minus P. And let me expand it in Legendre polynomial itself. Let me also do this. Go back one step. Sorry. I want to integrate this over the angle of K minus P over 4 pi. So I integrate it over solid angle. I want to take this interaction as a function of angle between K and P, and integrate it over solid angle. And convolute it with PL of cosine theta. So essentially, it's inverse Legendre transformation. And I get MPF over 8 pi square, and then minus 1 to power of L to fourth power. Plus terms e to minus L. Let me assume that L is large. I didn't say this before, but let me at this stage assume that L is large. Then this is the main result. Where it come from? It comes from this singularity. This you can check. If you would have a regular function, take any regular function of K minus P, convolute it with Legendre polynomial, and integrate over solid angle, you will get e to minus L. Because of singularity, you get power law decay, L to fourth power. Odd as a function of L. Why I'm doing this? Because remember what I need to do. I need to compute L component of this interaction, right? This is my goal. So let me write down now what is L component of this interaction. What I will do, I will calculate all this diagram, then I convolute everything with Legendre polynomial, integrate over the angle, which basically take inverse Legendre transformation, and I obtain components. And the result is that if we take this component AL, UL, like, right? Here is what the result will be. That L equal to even. It will be even equal to 2m. U bar L, did I call it? No, because UL, I'm sorry, UL. How should I put U tilde L to distinguish it between bare interaction and irreducible one? So this is now my irreducible interaction. I have to substitute in this formula everything by irreducible interaction because, again, this comes from summing up Cooper ladder. Transformation from U to U tilde is summing up all irreducible diagrams, the ones that transform interaction into some other interaction. What is some other interaction? U tilde L is equal to 2m, even. U 2m plus component of the bare interaction, right? Plus, interesting result, 2u square of pi minus twice u of 0, u of pi, minus u square of 0. And then let me call this quantity SL. I hope I will not confuse you with one formula. There will be M as counting of L. Even L is equal to M. It has nothing to do with the mass that's standing here. That's why I want to avoid twice appearance of M in one formula. Times SL, S to M. And U of 2M plus 1, odd L is equal to odd. 2M plus 1 will be equal U to M plus 1 plus twice U square of pi minus twice U of 0 U or pi, now plus U square of 0, S to M plus 1. So this is the result. I obtain this result as a result of second order. And Kohn-Lattinger did better than what I told you. They said, again, let's do it in 2 stages. Let's sum up all regular graphs and change U into U double tilde. And then on top of this, let's include singular contribution that come from the singularity in the polarization bubble. So in that language, this will be some U double tilde, and this will be also U double tilde. It's probably enough what we're doing. So here is what we have. First of all, that is unknown to us. But this is a regular interaction. We expect that this will be completely analytic function of Q. As a result, at large L, U to M goes as e to minus 2m, and U to M plus 1 goes as e to minus 2m plus 1, which is another way to say that partial component of regular interaction at large angular momentum goes exponentially, becomes exponentially small with angular momentum. This guy is power law. So then at large value of angular momentum, no matter what Bayer interaction was, no matter how I translated U into U double tilde, etc. Z is exponentially small. This is power law. Then this term is dominant one. And its universality in two aspects. First, it tells you that the result does not depend what original interaction is, except that there is a combination here. U of pi means, sorry, I have to be more careful, I put U of 0. This is U of q, which I translated as U of theta. U of 0 is equal to U of theta equal to 0. U of pi is U of theta equal to pi. On the Fermi surface, yeah. So this is K and P parallel to each other. This and K and P anti-parallel to each other. Sorry? In practice, it's 2kF, right? In practice, it's 2kF. So this U of 0, this U of 2kF, if you want to put it this way. Yes, please.
K minus E equal to 0, then it will be divert.
Say it again.
So I presume U is the Bayer interaction of the Coulomb 1 over Q squared.
Right.
So when theta is equal to 0, that Q goes to 0. Shouldn't it divert?
You integrate it over the angle, this integrated interaction, and always, just to avoid unnecessary discussion, always keep Yukawa renormalization into U. Then you avoid any discussion about possible singularities, etc. Then you get regular interaction, which is completely analytic again, and expansion is regular. Yes?
Right there in the graph where you don't have bubble.
Which is the graph which I don't have bubble? This is bubble, this is bubble, and this is bubble. All of them are bubbles. Again, let me not spend a minute. This is bubble. Guys, just calculate it. See what the momenta are, and you find that this is a particle hole bubble with total momentum K plus P. If you want, switch this guy back, and then you immediately see that this particle hole bubble. Yeah, there was a question. Just speak a little bit louder. You again run ahead of train. I was going to say this phrase next one. Really, you came ahead of me. The one question. You know everything. Yeah.
I just want to ask about this U of pi squared minus, like, it looks like it's going to be negative if U is decaying.
Just hold on a second. Hold on a second. So first, you said it absolutely right. I was going to say this. Where is the wonderful universality here? It's really, and this is what people didn't realize when they originally wrote these formulas and then used it. This is hidden one-dimensionality in three-dimensional system. This only comes from backscattering, or in fact, this is not, strictly speaking, forward scattering, because K minus K. So these two U of pi and U of 0 are spin and charge components of backscattering. You will see when I write the interaction in terms of spin and charge component, you will see it. Forward scattering is interaction that is KK, KK. We don't have this because we have minus K here. So even if we scatter by 0 momentum, we still give total momentum equal to 0. Scattering, 0 momentum scattering with total momentum equal to 0 is backscattering. There are two components, one is spin and one is charge, but this will come later. You're absolutely right. This is example of hidden one-dimensionality in three-dimensional systems. There are processes that know only about scattering when I scatter forward, or so when I scatter at 0 momentum transfer, or I scatter with 2kF momentum transfer, which means I go back. And there are some, you can go forward with this and then understand that even if you go to higher orders, you still express everything in terms of this will be fully dressed interaction at pi. This will be fully dressed interaction at 0. We can take these two components, rewrite them in terms of spin and charge components of backscattering, and then make the statement that everything is super universal. This number one. Number two, again, which was number 0, actually, is that, again, at large L, this term and this term are totally irrelevant, so we can forget about them. We still have unknown terms here. We don't know what they are, right? But we know this guy. We know that it's odd in M, right? It changes sign between even and odd L. And now question to you, particularly in view of your question. What's the sign of this guy? I don't know what's U of 0, what's U of pi. I just have no idea what they are. What's the sign of this guy? Positive. Why? It's the sum of two squares. It's U of pi minus U of 0 squared plus U square of pi, right? So no matter what, I don't know again, what are these two components? This is positive. I cannot say this about this term because this comes with plus sign, this comes with minus sign. So then I have to be careful. And Conner also didn't say anything. But let's look at this. So odd channel, right? This guy is positive. What about S? Odd channel. L is odd. S is negative. So overall sign of this is negative. And this is the main statement. No matter what you do, if it's isotropic system, as long as L is large, you're guaranteed that odd component of the interactions are negative, means attractive. This is all you need for superconductivity. This is what's called Conn-Latiger mechanism of superconductivity. We can't give a lecture without jokes, right? So let's tell a story. So
before you start your joke.
Yeah.
So the U tilde is U plus that bit, right? So, and you argued that the parentheses times the S is negative.
So what I'm saying is this, it's also U tilde, right? Of course. What I'm saying is that this guy, forget about this one, is exponentially small.
Oh, okay.
And this guy is negative, right? Right. So UL tilde, U2M plus 1 tilde is negative. Now the question is, if L is large, and you get this as goes to as 1 over L to force, right? You get your effective interactions that goes as 1 over L to force power. It's great for theorists. We can say, well, great, we get attractive interaction. But for practical purposes, if you want them to put this into exponent, you know what you get. You get e to minus 1000, right? Which is 0. It's no use of this, completely no use of this. So the question is, down to what M this is attractive? What's the practical realization of all this? And you cannot say anything here. And as I said, this is rigorous stuff because all regular normalizations are included here. This guy is just unknown for fully renormalized amplitude at momentum pi. But so we cannot say much. But very quickly after the original work, people started saying, let's look at this differently. Let's look at this in a little bit less rigorous way, but in a more practical way. And more practical way will be like this. Yes, let's look at smaller L. L is of order of 1. And let's view these diagrams, not as something rigorous when every wavy line is just summed up into all contributions which are regular and doesn't contain this singular normalization, but as just interaction. And then let's ask, what happens if we just do it? And the first question you may ask is, what about Hubbard U? We may say, well, in Hubbard U, there was only S component. There was only singlet when we took U to first order. But when we go to second order, even if interaction with Hubbard U, this guy, this guy, this guy, and this guy, they all give you function of momentum transfer. And as function of momentum transfer, they give you contribution which will be odd and even and K and P. So they will give you both singlets and triplets. So first question to answer is, what if interaction U, constant, original interaction, not U tilde, not what you have here. Then it turns out that this interaction, in terms of Legendre polynomial component, has only one component, L equal to 0, right? Constant has only one projection on the Legendre component. So this was L equal to 0 repulsion. We can calculate correction in L equal to 0 channel. And it turns out they're also repulsive. So we get repulsion plus repulsion. This is original, this is from the interaction. Now let's go to channels when L not equal to 0. L not equal to 0. Then we start with 0. And then what goes after 0? Well, we need to calculate. It turns out that if you do these calculations and do calculations to second order, you get attraction for all L not equal to 0. They are all attractive. Obviously, then the question, which one is the largest of them? I don't want to have attraction which is 10 to minus 3. I want something sophisticated. It turns out that the largest is P wave, L equal to 1, and the value of coefficient is this. Again, it's second order in U, right? So the U tilde, where is this? Yes. U tilde 1 is equal to minus U square times MPF over 2 pi square is nothing but extra U times density of states times 2 log 2 minus 1 over 5. Fortunately, 2 log 2 is larger than 1. So this is really attractive interaction. So P wave. So then in this respect, the story is very simple. If you have a system with Hubbard interaction, if interaction is repulsive, you get this. If interaction is attractive, yes, you get S wave. It's U. It's original term, and this is still perturbation theory. Now a joke, right? A joke is about, actually, is art to be honest. So when Kohn and Lattinger wrote their paper, they did this wonderful calculations, which was very much, they didn't talk about one-dimensional physics embedded in 3 dimensions, but they obtained all these formulas. So the formulas were there, they made the point that yes, it's definitely attractive, but then there was a question, practical applications. It was 1965. And at that time, for reasons that will take us 5 minutes to discuss, community believed that pairing in helium-3, for which superfluidity in helium-3, pairing of uncharged particles, we didn't talk about charge at all, was into state with D-wave pairing symmetry. Now arguments why it's D-wave are all gone, but at that time people believed that it was D-wave. So what they did, they had the full expression, they calculated the full integral, not only this quantity. All they have to do is to calculate the full polarization bubble, and that's it, and expand it in the Legendre harmonics, right? So the new result for all harmonics. They showed the result for L equal to 2. It was attractive, right? I said, all components are attractive. But component L equal to 2 actually already pretty well fitted into this formula. Sometimes you ask, what is the minimum L when this expansion formula works? L equal to 2 here. So what they found was that U tilde scaled as 1 over L to 4th power. And L equal to 2 means that there is a factor of what? 2 to 4th power is 16, right? And then you put it in the exponent, right? So they took APF like in helium-3, which was not small. APF was equal to 2, which is not bad. And so they obtained TC, which was, I guess, e to minus 40, something like this. Something like this, times Fermi energy. I don't remember exactly whether it was 40, but it was anyway close to this value. Wonderful. Everyone said great. Wonderful theoretical work. Let's do something else. Look, 10 to minus 40, right? They had the full formula. They did not, and I guess it was basically art how you do rigorous theoretical work at that time, to say that everyone says that it's D-wave pairing, so let's apply to D-wave. They had a formula, right? Full formula. All they had to do is to take Fourier transform or inverse Legendre transform. So if they did it for L equal to 1, their formula, U tilde of L equal to 1, gives Tc, which is Fermi energy, 10 to minus 3. This, I guess, this is 10 to minus 16, something like this. Or e to minus, e to minus, it's 10 to minus 40, I'm sorry. If Fermi 10 to minus 40, e to minus 16, read. And this is 10 to minus 3. And you know what's Fermi energy in helium-3? Something like 2 electron volt. 2 Kelvin. I'm sorry, I said something wrong. Or 2 MeV. 10 to minus 3 give you, sorry? 20 Kelvin. Right, you took it and 10 to minus 3, and you get millikelvin. This is exactly what the critical temperature was for helium-3, which was found 2 years later. And I only wonder if they put this formula in the paper and said that they predict P-wave pairing in helium-3 with the temperature of the order of few millikelvin. Well, the prices may go in a different way. This was obtained 3 years later by Fein-Lauser, and then people started basically using this formula later on. But what was interesting, and I want to make it not as a joke, but as an interesting example of what people were doing in mid-60s, and I really call it super honesty. There was a short PRL in which all this was presented. After that, there was a long PRB by Lattinger alone, in fact, with the thanks to Kohn, in which he presented the formula for L equal to 1. But then statement was, now we apply to experiment. And in experiment, it's D-wave pairing for helium-3. So we apply the formula for L equal to 2, and he presented this formula. He didn't say, they had a formula. So all I had to do is to write down one phrase, that if it would be L equal to 1, this would be the formula. This would be the result. They didn't do it, or he didn't do it.
Why did they think it would be D-wave, not P-wave?
Oh, don't ask me now, because it will take, I'm approaching already the end of the talk. So yeah, I can't tell you why it was, but because I heard this from Pitayevsky. He told me the story why people in 1965 thought that it was D-wave. It's all gone. Okay, now where are we? We are in a situation when essentially we said if the system is isotropic, there is an old scenario how to get superconductivity. And this scenario was with us for a while. And then starting from cuprates and then pnictides and then etc., people talking about lattice system where you cannot apply this reasoning. Why? Because in any lattice system, you don't have angular momentum as a quantum number. You only have discrete symmetry of, you cannot rotate by arbitrary angle. There is only rotation, symmetry for rotation with respect to, say, pi over 2, etc. So it's all discrete symmetry, which means that there are only discrete numbers. Sorry?
5 minutes.
Yeah, I said it a minute ago. Yeah, I know that 5 minutes. So there are only discrete representations. As a result, that reasoning does not work. However, the same reasoning viewed differently works. And this reasoning viewed differently is this. Don't look into superconductivity by taking your Bayer interaction. Renormalize your interaction in a non-superconducting channel, which in practice means renormalize it in a particle-hole channel, see what you get. You may get component of interaction that were not present in your original model, particularly if you take Hubbard model. Hubbard model obviously give you only a component in a completely fully symmetric channel. For example, in a system with square lattice, which has D4H symmetry, they have 4 one-dimensional representations and 1 two-dimensional representations, so 4 discrete representations. What is called A1G, and this is where Hubbard U plays a role. There is nothing in what is called D-wave channels, B1G and B2G, as well as, I guess, I channel, which is A2, product of B1 and B2. And then the story was renormalize interaction in particle Hall channels, see what you get in new channels. Because obviously, fully renormalized interaction will have components in all channels. And the first answer that came immediately from this kind of consideration, and I'm approaching the end of the story, so let me just state it, and maybe next time I will start with a few phrases about this, that if you have a system with a square lattice and cuprate-like Fermi surface, meaning that on a square lattice, you have Fermi surface like this, all details aside, but density of states is important in this corner, density of states is important in this corner. Important means the largest in this corner. And now you play the game, the same stuff. You want to start with Bayer interaction, which is Hubbard U. You want to see what your U tilde is. Interaction renormalized by the same graphs in a particle Hall channel. Then you do it perturbatively to second order. You find that U tilde has D-wave component, and D-wave component is attractive. So you immediately get pairing symmetry that was detected by people sitting at the last row. Then Dessau was the pioneer of experimental detection of D-wave superconductivity in the cuprates. So D-wave comes immediately from this line of reasoning. And again, second order, no fancy stuff, nothing. We'll discuss about how you transfer to more fancy things. You look into iron-based. Iron-based. These are systems which has Hall pockets in the middle, electron pockets at the corner. Number of these guys is 2, number of these guys is 2 or 3, but it doesn't matter. Because even in the simplest case, when you say instead of these patches where density of states of largest, I just take 1 Fermi surface here and 1 Fermi surface here. For Hubbard interaction, I again have only repulsion in S-wave channels. There will be nothing. But you do this, so everyone calls it still Conn-Lattinger type calculations. It's not Conn-Lattinger. It's not what they did, but it's fundamentally like Conn-Lattinger. So I renormalize my interaction in a particle Hall channel, and I want to get irreducible, fully reducible interaction in a particle-particle channel. It turns out that this guy gives you attraction in what is called S plus minus channel, and also attraction in D-wave channel. Comparable. Then you have to do practical thing. You have to do calculations for really 2 Fermi surfaces here, 2 Fermi surfaces here. In most cases, S plus minus win. But they have 2 attractive channels. And they all come from this stuff. There are more exotic things. On a hexagonal lattice, when you do these calculations, you find that there are 2 D-wave components which are degenerate by symmetry, and they all become attractive because of the same mechanism. And then you go below the critical point to see how these 2 D-wave components are arranged. They arrange with I factor. So you get a state which is chiral with break time reversal symmetry, which have Majorana state in the vortex core. So you have all beauty of this modern physics. And so what I was trying to do today is to tell you that starting from essentially splitting interaction into spinlet triplet, and then further splitting into angular component, you find the possibility generally that, quite generally, sorry, not to find the possibility, but quite generally, there is attraction, at least for large angular momentum of these components, if the system is rotationally invariant. If the system is on a lattice, I want to say one phrase at the end. There is no theorem that you always do Kohn-Latinger calculations and get attractive component. We know example with non-twisted but graphene in a displacement field, which has, in the limit, which just has SU4 symmetry. You write down Kohn-Latinger normalized interaction. It has all components repulsive. You need to break SU4 symmetry to get attraction. But most of the cases, you find attractive component. And these attractive components, surprisingly, are consistent with most basic experiments in materials that are under study. D wave, dx squared minus y squared. In the cuprates, S plus minus, or possibly also dx squared minus y squared. In iron-based superconductor, less with experiment, but still interesting, D plus ID. In hexagonal systems, number of experiments about what, a number of theory works about what happens near Van Hoff points. Let me not talk about this, otherwise I will not go into dynamics, which I want to do. Okay, now the last statement for today, before we all go for lunch. Last statement of today is that this is, you may say, well, you're talking us about something else, and people are saying this is a pairing by spin fluctuations. This is pairing by spin fluctuations. My last statement for today is Kohn-Latinger diagrams like this is the lowest order diagram for spin fluctuation mechanism. I will show you next time, I will start lecture with this, how to go from these diagrams, sum up particular series, and get interaction mediated by either spin fluctuations or charge fluctuations. But one interesting thing I want to emphasize, if you have attraction in D channel, it's already there at second order. What spin fluctuation do? They just enhance the strength of this attraction, but don't do anything else. So in this respect, it all comes from the same source, and the source is this one. Essentially, renormalizing of your Bayer interactions into fully reducible interaction in a particle-particle channel. And the rest will follow from there. Let's stop here, and then next time we'll still do RG, because I think it's a fantastic thing here. And then we go to dynamics and discuss pairing near a quantum critical point and all non-familiar with stuff that accompanies this pairing. Okay. If you don't mind, yeah.
Your final moral, I've heard people say sort of qualitatively that Kohn-Latinger, you will never see an experiment because it's so exponentially small. But the moral that you're saying is that it's always there, and when people say, oh, it's due to spin fluctuations, I should actually think of that as an enhancement of...
Exactly.
My question is, could I ever observe your Kohn-Latinger superconductivity experiment? Has anyone ever seen that? How would I know?
Ooh. In some, well, I will go into say P-wave pairing in helium-3, but even there, it's at least for some part of the community, it's essentially pairing by ferromagnetic spin fluctuations. It's again, it's Kohn-Latinger, but sum up infinite series of graph enhancement by, so pure probably no, but enhanced, yes. And then you need to ask yourself whether it's, you view enhancement as a new physics or just really enhancement, number is larger. Because there is nothing wrong about where I have this wonderful formula. Yes, there is nothing wrong about this, except that even if you put these numbers, well, you get something like 10 to minus 3 of something. Yes, but to get 10 to minus 3 of Fermi energy is not that bad. Yeah, the only thing that, to be honest, we don't know prefactor. Prefactor has not been calculated despite efforts. There is some effort to calculate prefactor, but it's not entirely complete. Just one and two. Go ahead.
Okay, so yeah, in your renormalized interactions, like in all channels, so you said that in large L limit, the interaction correcting terms dominate over the pair term. But then in this case, how do you know that the perturbation theory still works?
Oh, because I'll tell you, this is Kohn-Latinger. They say that you can rigorously calculate prefactor for 1 over L to 4th term. And again, let me just repeat, probably I already said this, it's just what they said. We don't know what this guy is. It's not U of pi. It's actually fully dressed scattering amplitude with momentum pi. This is fully dressed scattering amplitude with momentum 0. So we don't know these components, but we know that this is positive, no matter what this u of pi and u of 0 is. We know that this is negative. That's enough. This is why they never made any statement about even L channel, because this sign of this guy, you don't know really. It can be potentially either positive or negative depending on the interplay between these two guys. This is not full square.
Jupiter has D wave and Atlas has A and D. Does this difference come from the different singularity in the polarization puzzle?
No. It's the same. S plus minus is the same as D. In fact, what happens is that, what is D? D means that if it's plus here, it's minus here. It's a patch model. One patch is with plus sign, one patch with minus sign. Here is the model, instead of patch, you get Fermi surface. It's plus here and minus here. So if you want to call this patches, it's the same story, plus and minus. But because this is Fermi surface, you make a circle around gamma point and nothing changes. This means that it's S. So it's what's called sometimes it's S in name only. It's like D, but between Fermi surface. You just calculate to second order. What you get is this. I will actually talk about this case tomorrow morning, right? And then we'll see where it all comes from. Yes.
Do you get anything different if you go beyond second order?
Good question. In any spin fluctuation mechanism, we actually go to infinite order, but you choose a particular set of graphs. For example, I will just say one phrase, if you don't mind, just not to write down. In order to get any spin-mediated interaction, you forget about all these terms. You take this one and then write maximally cross diagram. This gives you spin-mediated interaction. If you want charge-mediated interaction, you go with this guy and sum up infinite series of graphs. Neither I nor anyone else know how to do it more accurately. And this is a statement that there is no way anyone knows how to derive interaction mediated by collective excitations. Either you do it approximately, like choose a particular set of graphs that sum them up, or say, forget about everything, I take it from experiment.